Okay, I'm aware that this class will last only until 9:30 since there was people who had class at that time. So don't worry, I'll stop at 9:30. So let's go on to the next topic. And the next topic is, okay, tertiary behavior of the structure. And in this case, this is a figure that we use at the beginning of the previous subchapter. This is the combination, as you can see here, plate, stiffeners, girders. And in here, we can identify a piece of plate between stiffeners and girders. And that's what we consider our tertiary structure. Since it is a plate, okay, we can go back to chapter 4 and we could try to find the thickness, okay, which solve this equation in such a way that the pressure will generate an stress which is below an acceptable limit. Okay, that's the idea of design. Okay, now in this case, okay, we could assume, okay, that the edges, 4 edges are clamped. Now, this is just an extreme situation, but it's a good as a reference. Okay, in that case, we could consider that, for example, in this direction, there would be no slope. And in this direction, for these other edges, this and that, in this direction, also the slope has to be 0. Okay? That means that we could assume that this, each one of these plates is clamped completely on the 4 edges. Okay? That's a model for this problem. The problem with that is that we have to accept that the stiffeners deflect and also that the stiffeners rotate. That means that the boundary conditions of the clamped boundary conditions for the edges of the plate are not completely correct. We can take them as clamped as a reference, but that's all. They are not really clamped. Okay, so the stiffeners, they deflect. And once they deflect, there's a redistribution of the bending moment distribution in each plate. Okay, so we have to have that in mind. Now, let's, just as a reference, okay, let's remember some of the details that about the response of a clamped plate under uniform pressure. And of course, the name Timoshenko comes to our mind, okay? This table is taken from this reference here, okay? It's a classical book, Theory of Plating Shells. It's a very old classical book, okay? And here, remember that you have to be careful because the reference system is located in the central point, okay? B over A is larger than 1 for this solution. That means that B is larger than A. Remember, we have to be careful when we use any reference that presents a solution, okay? And in this figure, you can see that Q represents the pressure instead of P. And it is uniform, as you can see here, uniform loaded, okay? So we have to be careful with that, but that's all what we need to do. We remember that in the direction of the shortest side, that's the A, okay? In this direction, we have the larger bending moments, okay? In this direction, okay? And that's the MX, okay? Okay, so remember when we started this study, what we did was we put it our thumb in the y direction, and that represented mx. So that's what we're doing, okay? Now, so we could expect in this point to have a larger bending moment, larger than in the center. And also, the sign will be opposite. Similarly, the bending moment here, mx, is going to be larger than here and opposite in sign. And of course, yes, if the four edges are clamped, we could expect the larger deflection to be in the central point. Okay, so Timoshenko provides this table according to the aspect ratio of the plate. So here, this is the expression that you could apply in order to have or calculate the deflection in the central point. You see that x equals 0, y equals 0. That's this point here. So according to the aspect ratio, according to the pressure, this is the minimum dimension, and D, you can estimate the deflection in the central part. And you can use these four columns in order to estimate the bending moment here, or in the center, here, or in the center. One is mx, my, mx, and y. Okay, and you can compare, for example, this is the center, this is the center. If we can compare mx in the center, and this is in this side, x equal a/2, so it's in this point here. Okay, you see that the sign is negative, while this sign is positive. This is something that we were expecting. And not only that, but this value, 0.08, is basically twice this value here. Okay, so this is the larger stress, normal bending moment, which occurs in this point, has different sign as this one here, and its value is basically twice this one here. Okay, so this is the position that we should be willing to analyze if we could assume that the plate would be completely clamped. Okay, now, after we have found the bending moment, okay, we could evaluate the maximum stress. It is either at the top or at the bottom of the plate. So the position Z would be equal to plus or minus the thickness divided by 2. And if we replace that in the expression for the normal stress, this is the result. Now, this, again, this would be the expression if we were interested in analysis. Okay? In this case, we would have the thickness and we would calculate the maximum stress. If we want to design, okay, a plate, in that case, we have to select the thickness. We know the pressure, and we have to set or select a value for the maximum or permissible stress, right? So this is given, this is coming from the sketch, and the result of this will give you a value for the thickness. Again, we will see that we have a to the square, so the square root will give you an a, is square root of p, square root of sigma. And we're going to deduce something similarly as we did for the section modulus. For that's the expression for the thickness as function of this dimension. Now, again, we could do a similar dimension analysis, because usually the pressure is given in kilonewtons per meter square. Sigma is usually expressed in megapascals, and usually the thickness is expressed in millimeters. But we could do something similar, okay, similar analysis, and we could compare the expression that we can deduce from this this equation that comes from plate theory, and compare it with the expression that is provided by the classification society rules. And it's quite similar, as we will see, except that the maximum value we have to discuss a little bit, because as we accepted, okay, the clamped plate model, it's a good one, but it's not so efficient, because we have to accept that the deflection of the stiffeners and the rotation of the stiffener affect the distribution of the bending moment. Okay, we will discuss that tomorrow, and when we continue this lecture. And again, I would like to thank you because of your patience, and we stayed here with me until I finally was able to come to start this session. Okay. Thank you very much. And yeah, I'll see you tomorrow at the usual time. Unless there is
Doctor, sorry.
a final question.
I got a question.
People?
Yes, doctor. I have a question. Well, I would like to say something if it's possible. Sure. Could you consider giving more time to present assignment 6, if it's possible?
Assignment 6. When is that due? When is that due? When do you have to complete it?
On the aula virtual classroom is for tomorrow.
Yeah.
It's tomorrow. Tomorrow is
Tomorrow.
Friday.
10. Yeah.
Okay, I can expect until say at night, Friday night, because I have to give you another assignment. Okay, I can expect it until Saturday. Okay, I can change it. Okay, I'll change it right now. Okay, I'll change it right now, so I can move it for Saturday. But remember that you still have one more homework, because you need to practice secondary, tertiary, and the combination of stresses.
Okay, doctor.
Okay, no problem. No problem.
Thank you.
I assume you're talking by as for the rest of your teammates or your classmates, right?
Yes, doctor. Thank you.
Okay, no problem.
Doctor. Thank you.
Okay, you can stop the recording.